In this video, I want to develop the notation that we need to describe the product of two arbitrary polynomials in a polynomial ring. So we are going to let p of x be this polynomial, which has degree n. And we're going to let q of x be this polynomial, which will have degree m. And what I'm wanting to notice is that I'm wanting to find a way to describe the polynomial p of x times q of x. Now, I already know a bunch of things about this polynomial. I know that its biggest possible power is going to be created by multiplying these two terms together. So it's going to start off with an a(n) bm times an x to the n plus m. And I know the very smallest thing that I'm going to get, the constant of the product polynomial, is going to be the product of those two constants. So I can write that way down here as a0 times b0. The question, however, is what goes here? Now, I do know that if I had been given two explicit polynomials and they didn't have too many terms, I'd be able to line them up and do a actual computation of the product by finding partial products and adding those partial products together. And that's essentially what we're going to be trying to do in a more general setting. Now, it turns out that in order to build the formula for what goes in that missing spot, I'm going to want to actually turn these two polynomials around and write them from the constant up to their leading term. So I want to think about p of x, and let me get back to my normal color. I want to think about p of x as being a0 plus a1 times x all the way up to an times x to the n, and I can write that in sigma notation as I goes from 0 to n of a sub I times x to the I. And likewise, I can write q of x as b0 plus b1 times x plus all the way up to bm times x to the m, and that in sigma notation would be I goes from 0 to m of b sub I times x to the I. And I know something about my target product polynomial. My target polynomial is going to start off with a0, b0, and then it's got all kinds of stuff that I don't know how to figure out how to write just yet, but it ends with an a to the n times b to the m raised times x to the n plus m. And I can at least symbolically think about this as being a polynomial as I goes from 0 out to n plus m of some unknown coefficient ci times x to the I. And my question is, how can we find ci? And I want to think about that, and I'm going to rewrite my two polynomials in order to figure out how to find that ci. So here's p. And here's q. Now, the first thing I'm going to do is I'm actually going to fatten both polynomials up to arbitrarily look like they were polynomials of the same degree. And so this would be 0 times x to the n plus 1 plus 0 times x to the n plus 2. And this is going to go all the way out to 0 times x to the n plus m. And I am going to fatten this one up in the same way. So we have 0 times x to the m plus 1, 0 times x to the m plus 2, all the way up to 0 times x to the n plus m. And my notation convention with this red stuff is going to be that a sub l is going to be equal to 0 for l bigger than or equal to n, and b sub l is also going to be equal to 0 for l's that are bigger than or equal to m. And essentially this lets me think about both p and q as being polynomials that have up to x to the n plus m in terms of powers of x in them. Now what I want to do is I want to think about how do we create an x to the I term. Well, when I'm looking at all of the partial products, essentially every single partial product in the product polynomial is one of these terms times one of these terms. And if I'm looking for an x to the I, the term that I pick up here, wherever it is, the term that I picked from the p one, has an x to something, so I'm going to think about that as an x to the k. So this is from my p polynomial. But I actually know that the coefficient of x to the k is going to be a sub k. And in order to get an x to the I, right here, if I've picked x to the k from this polynomial, I have to have an x to the I minus k from the q polynomial. So I must be multiplying this by something that has x to the I minus k, but I know that the coefficient of that will be b to the I minus k. And this is going to be nothing more than ak times b to the I minus k, and the power of x is going to be x to the I. Now if I think about this, that tells me exactly what I need to know. All I have to do to get the coefficient of x to the I, so the coefficient of x to the I in the product polynomial is going to be the sum of these guys. And that sum is going to go as the k starts at 0 and goes all the way up to I. In other words, to kind of go back looking at the polynomial, in order to create an x to the I term, I have to pick an x to the I or lower power of x from the p polynomial. And that's what's telling me that this k is going to have to be trapped between 0 and I inclusively. Well, what this means is that I can actually write the coefficient of xi down explicitly. The coefficient of xi inside my product polynomial is going to equal, let's see, it'll start off with a0 times b to the I, and then it'll have a1 times b to the I minus 1, and then a2 times b to the I minus 2. And we will keep going until we get up to a to the I minus 1 times b1, and then we will have an a to the I times b0. Now we can shorten this notation quite a bit by writing it as a sigma notation. This is going to be the sum of ak times b to the I minus k as k goes from 0 to I. And that is the coefficient of x to the I inside my polynomial product. Well, that tells me that I know how to write the polynomial down now. So what I can do is this. My product polynomial will look like the sum as k goes from 0 to 0 of ak b to the 0 minus k times x to the 0 plus the sum as k goes from 0 to 1 of a to sub k times b to the 1 minus k, and I want to multiply that by x to the first power, and then I'm going to have the sum as k goes from 0 to 2 of ak b to the 2 minus k, and that will be the coefficient of x squared, and I keep going, and eventually I get to the sum as k goes from 0 to I of ak b to the I minus k. That's the coefficient of x to the I, and we continue on until we get to the very last term, which will be the sum as k goes from 0 to n plus m times a to the k times b to the I minus k times x to the n plus m. Now, it is important to realize that in this expression, AL is always going to be equal to 0 if L is bigger than N, and B to the K minus L is going to be equal to 0 if K minus L is bigger than M. And so a lot of these terms, particularly the higher powers of x's, are going to drop out of the sum, but we don't need to worry about that because that'll take care of itself. The net result of this is, however, that we can shorten this thing up even more by realizing that this is when I is equal to 0. This mess is when I is equal to 1. This mess is when I is equal to 2. This, of course, is my general term, and this is when I is equal to n plus m. So what this allows me to do is it allows me to write the following. We can write P times Q as the sum as I goes from 0 to n plus m of the sum as k goes from 0 to I of ak b sub I minus k times x to the I. And it may help to put some brackets around here to realize that we are summing on this particular thing times x to the I. And you should be looking for this kind of general notation. So this is the general notation for the product of two arbitrary polynomials.